guys, it's Dakota Wixom here from QuantBros.com. Thank you for downloading our R Programming for Finance Bootcamp. This is Part 1, Financial Programming and Time Series Basics. If you've never used R before, you're in for a ride. It's a lot of fun. It's a statistical programming language. It's being used a lot on Wall Street nowadays. I know I'm going to be using it a lot. All right, so to kick everything off, I'm going to tell you what we're going to be learning during this tutorial. We're going to cover a lot of content in this course. We're going to go through the basics of R programming, downloading R itself, and RStudio. RStudio is kind of the interface for R. R is the programming language. We're going to talk about using data frames for financial time series data, an intro to the Quantmod package in R, which does some really cool stuff, especially for finance. We're going to talk about reading in financial data from Quantmod, using vectors in R, which is a simpler data structure than a data frame. We're going to talk about reading and writing data as CSV files, plotting time series data in R, working with split and dividend adjusted data for finance specifically, calculating log returns from price time series, converting log returns to arithmetic or simple returns and vice versa. Of course, you're going to learn what all this means later if you don't know now. We're going to use the apply function in R, which is great for working with multivariate data. We're going to talk about the performance analytics package, which again does some really cool things in R. It's super useful for finance. We're also going to cover the XTS and zoo objects. Same thing, very important for financial data. And we're going to talk about how to chart cumulative returns for an asset, draw down daily returns, multiple assets at once, and merging different data sets with different indices. Maybe they are trading on different days. That could introduce a whole new host of problems, and R has some really great ways to deal with that. We're also going to teach you how to calculate Sharpe ratios and other performance metrics in R. And boy, that's a lot, isn't it? But honestly, once you start going through all of this, it's going to make sense. Everything is important. Everything that's in this tutorial series is there for a reason, so pay close attention if you haven't covered this stuff before. Alright, so first things first, we're going to go to rstudio.com. Really easy, go to Products, RStudio. And now, when we download RStudio, we're also going to have to install R itself. So RStudio is a development environment for R. R is the programming language. There's also another version of an R integrated development environment, which is what RStudio is, and it's run by Microsoft. So that one is called Revolution Analytics, which is pretty much a little bit better than R in a lot of ways. I'm not going to use it though. I haven't used it yet. I know it's very good for high performance computing, but for the sake of the tutorial, if you've never used R before, go ahead and go with RStudio. It's going to be much easier for you. So in order to install R, we're going to go ahead and click Download RStudio Desktop. Make sure you've got the open source edition. And now here, see this link? We're going to need R, so go ahead and open that in a new tab, and we're also going to download the binary that you need. So for me, I'm going to download the Mac version. If you're on Windows, do the Windows version. Ubuntu, oh dear God, smarter than me probably if you're running that. And so once we got RStudio downloaded, go ahead and install the R binary. It's pretty straightforward. You got to download the right package, and you shouldn't have too many problems with this. This is a little bit less seamless than RStudio's install is going to be. Alright, so once your package is downloaded, go ahead and install it. This version of R is called Wooden Christmas Tree. You might have something different. I think mine was before called Beach Ball or something like that. So the way you can think about R is the programming language itself. If you want to program in R, be my guest. It's going to be a little bit difficult. Hopefully you're familiar with command line tools and all this kind of stuff. But really the best way to go is installing a integrated development environment, otherwise known as an IDE. And for us, that's going to be RStudio. And that's how we're going to interface with R in the same way that you would use, say, Visual Studio to interface with C++, or maybe brackets or some other editor to write HTML or CSS code. Now, if you've never programmed before, don't be afraid. R is definitely a fun way to start programming. It's one of my favorite languages. It's used all over the place, and learning it now is definitely going to be a good idea for almost any industry. For us, we're going to use R because it's got a lot of different packages that we can use to deal with financial time series data. There's also a lot of different models that we can use that are pre-built, and you can build some really cool stuff right out of the box with RStudio. If you install the right packages, you can do some pretty insane things without having to know too much programming. All right, once your R is done installing, you're going to want to download RStudio, install RStudio, then open RStudio. And again, make sure you open RStudio, not R itself, unless you want to program in the command line. So it's all downloaded, so we're going to go ahead and install RStudio. On a Mac, this is pretty easy. If you're on a Windows machine, I'm sure you know how to install programs, so I don't think it's going to be a problem. If you really do need help, though, I'm sure there's other resources you could find. Alright, once you're done installing RStudio, you may or may not need another update. R likes to push everybody to their most recent platform. It's kind of like a preview version of R. So you may or may not want to install that. Really, there's not going to be a lot of problems if you work in this version of R, but just be careful. In any case, I'm going to go ahead and ignore this update. So this is R. If you've never opened RStudio before, it's going to look like this. Again, make sure you open RStudio, not R itself, just RStudio. This is the development environment we're going to be working with. You've got a console here. You've got some things to the right, which you're not really going to have to worry about too much yet. You could do anything you want in this console. You could say 2 + 2 = 4, but you couldn't do multiple lines, right? You couldn't do 2 + 2, and then you couldn't do 3 + 3. It's just going to run it all together. Yeah, it's gonna try and run it all together there, so it doesn't make sense. So we actually used R scripts. So we're gonna go to File, New File, R script. Also, we can clear our console if you've got an error and you know that you're gonna not have to worry about it. You can press Control L and see everything in our console went away. All the variables that we have been working with would stay. Of course, we didn't actually assign any variables yet. I'm going to show you how to do that in a second. So now we're going to save our script. Just make sure you've got an R script saved. So we're just going to call this my first script.r, right? So now let's create our first variable. Let's call it A, and we're going to assign to A the value 2. Now, if you've been working with other programming languages, you might say, wait a second, shouldn't we do A = 2? That's actually the same thing as A, and then typing this little arrow, 2. The reason why we use this notation and not this in R is because of functions. So functions in R look like this. If we've got, let's just call it B equals func, and then you've got maybe a parameter var2 and var2 = 3. So we're assigning to B a function with parameters equal to 2 and 3. And if you had written instead B equals func var equals 2, it's confusing. What's being assigned to what here? That's why we don't do that. So try to stay away from this. Try to stick with this arrow notation. I know it's a little bit confusing and aggravating if you forget it, but everything's going to run just fine if you forget it. Just try to remember the reason why. that we do this. So now we've got our variable. If you actually want to run this line, you've got to select the line or just keep your cursor on the line and press run. The other thing you could do is click on the line again, press Command Enter or Control Enter, and that's going to run, and you can see everything being run down here in the console. If you want to look at a variable, just type the variable name into the console. A, enter, 2, right? Or we could type it up here and run the line. A equals 2. Perfect. Let's clear the console, Control L. All right, so now we're ready to go. Let's go ahead and clear the workspace. So this means that even though A is in our script here, if I type in A, it doesn't exist anymore because I've cleared it. So we're going to go ahead and create a data frame object in R. We're going to do that by typing df. That's just our variable name. We could call it whatever we want, but let's go with df arrow dash data dot frame. So df equals data dot frame. Now we're going to go ahead and run that line by clicking run, and then we're going to type in that object name again, df, and run that. And look, we've got an empty data frame, 0 columns and 0 rows. All right, so what is a data frame and how are they useful in R? Well, data frames are R objects. They store rows of data with a certain number of columns for each row. So let's say we've got an object let's say we're working with Apple's stock price over time. So we could have a data frame of prices, and maybe you've got different kinds of prices. You've got your open price, your low, your high, your close, your adjusted close. Maybe you've even got volume in there. And every single day is going to have those same attributes. Now, all of those attributes are going to stay the same across each of the days. None of the days should be the same, so none of the rows should be the same. In other words, every row should have a different name. You could add as many rows as you want. You can merge data frames. You can add columns or attributes to each of those days. Now, it doesn't have to be a day. It could be an index, could be anything you want as the row. And then each column has to be a specific data type. So if in column 1 you've got a bunch of dates, all of column 1 has to be a date. You couldn't pass in a number. In column 2, maybe you've got a bunch of numbers. You couldn't pass in a date. So just be aware of that. If that's a little confusing right now, it's going to make sense once you see the data frames in action. So we're going to go ahead and do that. We're going to actually install a package though first. So to do that in R, you're going to type install.packages, and then we're going to do in quotation marks Quantmod. And then I'm going to go ahead and run this line, Control Enter, Command Enter. Make sure that you run it. If you already have this package installed, it's going to prompt you to update, like me. All right, so everything updated, and now you're going to have to type library Quantmod, because even though your package went to the R repository and downloaded even though your install.packages function went to the repository and downloaded that package, it didn't actually apply it to your current work session. So you got to make sure that you type this library Quantmod line and run that. So now you've actually loaded that package. You're never going to have to install the package again unless you want to update it like I did. Alright, so Quantmod comes with a bunch of different functions for us to use that are very useful for financial time series analysis. So let's just say that we want to download Apple's stock price. So let's type in df equals data.frame get symbols, which is a Quantmod function, which is going to go to, say, Yahoo Finance or whatever the data provider is, to download Apple, which I put into quotation marks here. And then we're going to type auto.assign equals false. Make sure you do that, because if you don't, it's not going to store to this variable. Make sure you type in this line here. So we're going to go ahead and run that, and what that's going to do is go to Yahoo Finance, download all the data for us, store it into our df object as a data frame. right? So now we're going to type df in here, and you can see all of the data that we've downloaded. Now there's actually lots and lots of rows. You can see here it says omitted 600 rows. Well, there's a way that we can see the beginning and end of the data frame, because we don't know when this started, we don't know when this ended. Maybe it goes back to, I don't know, 2002, but I can't tell, right? I'd have to scroll up through all of this. What a mess. So R has some really handy functions. So we're going to type head of df, and we're going to go ahead and run that line. And there you go. There's the first few entries. I think it's the first 6 or so. Or we could type tail of df. So now we can see the last few entries. So now it's pretty clear. Our data goes back to 2007, and it goes all the way to 2015, and here's a specific day. Now, it may be different for you depending on when you run this, but that's not a big deal. You can see that we've got our open, our high, our low, our close price. We've got adjusted price, which we'll cover later if you don't know what that is, and we've got our volume for Apple stock. So just to make everything a little bit easier to deal with, I'm actually going to store to a new variable called AAPL, and to that I'm going to store the tail of df. So in other words, I'm going to take what was outputted here, these last 6 entries, so the last 6 trading days of Apple, and I'm going to store only that data to our Apple object, even though there was more data in df. So I'm going to do that using the tail function again, run that line. Now if I type AAPL, you can see that's all the data contained in the AAPL object. If you type class of AAPL, you can see it's a data frame, and within each column, now we've got our open, so all of the prices in the open are of the same data type, which is numeric. And that's actually, we've only got numeric data in this, but then we've got our rows to the left here, which are the dates, and all of those are the same format. That's the way that data frames work. So we can actually look at a single column of data of the data frame by indexing our object, and the format for that is just, and by the way that you type in comments in R is with the hashtag. So the format for that is just these little brackets and begin to end, and that's for row, and then begin to end, and that's for the columns. So apply that to our Apple object. So we've got AAPL. Now we're going to index the Apple object. Let's go from row 1 to 3. So that's going to be rows 1, 2, and 3, comma, columns. Let's go from from column 1 to 2. All right. So we're going to go row 1, 2, 3, and columns 1, 2. So it should be these 6 data points here. We're going to go ahead and run this line. And yes, that's exactly what was output. Handy dandy. Now we can actually index the properties of our object separately. So we could index, say, the first row, but use all the columns. So maybe we want the open, high, low, close, volume, and adjusted price for Apple on the first row only. So let's run that, and you can see that's exactly what we get. Maybe we want, for example, the first row and only the first price. So AAPL 1, 1, first row, first column, and that's exactly what we get. Maybe we want all of the rows and only one of the columns. So let's do AAPL for every row. We're actually going to enter nothing in the row argument, but we still need the comma. So nothing, comma, column 1. So go through all rows and show me column 1 for all rows. You could do AAPL, show me all rows, and show me columns 1 through 3. In fact, maybe you want to do AAPL, show me all rows, but you only want columns 1 and 4. Now this is actually a vector here, the C argument, and we're going to cover vectors shortly, but this is going to get you all rows, columns 1 and 4 only, instead of doing columns 1, 2, 3, 4 with the colon notation. And there we go. That's exactly what we get. Column 1 and column 4, and all of the rows are variable. So that's how we index data frames. In fact, we could actually index data frames by a specific day. So these are not actually attributes of the data frame. This is just the row names. So it's not actually a column. So we could say, let's look at AAPL on a specific day. So we're going to pass that into the row argument. So we're going to do quotation marks 2015-12-31 all columns. So give me all columns on that specific day. And there we go. There we have it. That's how you index with row names. So can we do the same thing with columns? Maybe I want to only look at Apple Open by name or Apple Close. Maybe you have like 100 columns, and so I need to pick a specific one. Well, we could do that, but first let's rename the columns because it's annoying to type, aapl.open, aapl.close, right? I named it Apple. I know what the object is, so I don't really need this prefix for each of the column names. Or maybe you just want to name it something different for each of the columns. So I'll show you how to do that. First, let's type call names of AAPL. And you can see those are the column names. This is actually a vector of characters. In fact, to prove that to you, I can do class of call names AAPL. And there you go. It says a vector of characters. That's different than the class of the Apple object itself, class of AAPL. And see, that is a data frame. All right, so you're asking now, what is a vector? Well, a vector is a series of values of the same data type. It's only a single row, so it's kind of similar to a data frame in that all of the values are the same data type for the data frame. That's just depending on the column. But for a vector, you've only got one of those, so everything's the same. So it's either a character vector, or it's a numeric vector, or a date vector, whatever it is, whatever the data type is. So in fact, each column or each row of the data frame is essentially a vector. A data frame is essentially a vector of vectors, right? You've got a bunch of different rows and a bunch of different columns, and with each row, you've got a vector of columns, or for each column, you've got a vector of rows. However you want to think about it, it's a data frame's multi-dimensional or basically two-dimensional, and a vector is one-dimensional. So just to illustrate this a little bit more for you, we can type AAPL, all rows, column 1. And you can see we've got a vector of numerics here. The class of AAPL, all rows, column 1, is numeric. It's a numeric vector. Now, what if we did AAPL for row 1, all columns? Well, that gives us a data frame object. Why is that? Well, that's because we've got a row name, and vectors can't have row names in them. So this is saying only give me, one dimension, only give me one day, but give me all of the values for that. But these could be different data types too. Maybe instead of open, we've got company name here. So this is not going to show up as a vector for us. But if you index by column, everything is going to be the same data type. So that's why if we index by column only, for a single column, it'll give us a vector. If we index by row only, for a single row, that's going to just give us a row object now, or a data frame. Now we could, in this example, force it to be a vector, because in this example, we've got all numeric values. So I'll just do as.numeric, and there you go. Now we've got a vector object of numeric values. And if you do class of that, you can see it is indeed a numeric vector. All right, so that may be a little confusing. Don't worry about it. You're going to get used to this over time. So I'm going to go ahead and delete everything up until this point. So now we've just got our Apple object, right? So AAPL, I'm going to type that in here. See our data frame again. And then remember, we were wanting to rename the columns of AAPL. And there we go, open, high, low, close, volume, adjusted. We want to rename that something different so we can actually assign to this attribute a value here. And now let's pass in a vector using the C argument. C creates a vector, and in that we're going to pass what we want. So let's say the first one's open, comma. Let's do high, and make sure you've got quotations around everything. Low, low, close, volume, and adjusted. All right, so we're going to go ahead and run this line here, and you can see we've got now, if you type in AAPL, the columns are renamed. Great. So now I can actually index the Apple object by column names really easily. I can say AAPL with the brackets, comma, let's do just the open. So this is going to say, give me only the open prices. There we go. It's just like saying comma 1, right? It's like the same thing as saying this. Because it's basically just saying, find the column with this name, and oh, that's column 1. Then it passes in here, and it runs that. Pretty easy. Now, what if we wanted, to do AAPL, comma C? Let's just say the open and the volume, right? So that's 1 and 5. All right, we can do that, but now let's do that with row names. So let's do AAPL, all rows, C, open, volume, and there you go. It's exactly what we did. It's the same value. So that's a great way to do it. You could type, AAPL of all rows, and then open volume. But this is going to give you an error because it doesn't know what the row is. It doesn't know what the column is. It really confuses R. So if I run this, it's going to say, wait a second, what's our index? It doesn't know what to do. So don't do that. Make sure you pass in a vector if you're going to work with it that way. In fact, we can even index our object by row names and column names at the same time. So let's do that right now. AAPL bracket, let's just say 2015-12-23, and it may be different for you depending on when you downloaded this, and high. So let's look at the high only for that day. And there we go. There's our value. Now I'm going to clear the console again, Control L, and that just gets rid of the error message because it was annoying me. So now we've got our object. We can actually write our data as CSV files. So remember, our DF object holds all of our data, right? So AAPL only holds a few prices, and our DF object holds everything. Look at that, lots and lots of rows. So we can overwrite our Apple object so it has all of the trading days. So let's go ahead and do that. So let's do AAPL equals DF, and I'm going to run that now. Let's run AAPL. Perfect. AAPL now holds all of our data. Awesome. We can do head of AAPL just to check everything out, and call names of AAPL. And look at that. So our call names are not the same. So now we can type in our names here. Let's do open, high, low, volume, and adjusted. There we go. And now we can check out our Apple object. Perfect. So now we're ready to output our data as a CSV file. Luckily, R is really good at doing this. We can just type write.csv AAPL, and then let's name the file. Let's say AAPL-data.csv. All right, isn't that easy? And the reason why you might do this is perhaps you've got, perhaps you've got a lot of work done, and you've found some data that you know that you're going to need later, but you gotta leave the computer, right? And you don't want to keep it running, so you could output something to a CSV file and then read it in later. So now that we've got our CSV object, we can read it straight in. So let's just do read.csv, and let's just call it aapl data.csv, right? The same name as we wrote before, and there we go. There's our CSV object. But see how it doesn't know that the first column is actually a row names column? That's because we haven't told it to look for row names. So we're just going to pass in another parameter to the function, row.names equals, and then what column? Well, it's the first column, 1. So now it knows. Now everything's stored properly here. In fact, we can look at that easier if we do head and run that and check it out. Now everything's ready to go. In fact, we could start from right here. We could get rid of everything else. We don't even really need anything else, and we could say apple equals this, right? AAPL, and there we go. We don't need anything else. In fact, you could clear the workspace if you just started from scratch. Get rid of all this. You don't even necessarily need the Quantmod package. Run this, and there we go. It's just reading the CSV file, and we've got all of our data. Now, in the code that I send you, I'm going to leave everything that I've done so far. I've commented everything out. It's going to be really easy to follow, but just for the sake of the argument here, I wanted to do this for you. All right. In fact, I'm just going to call this data. Data equals apple. All right, so let's plot our data. Plotting data in R is really easy. So just do plot and then our object, right? And nope, just kidding, because we've got a lot of data in this object. In data, we have, what is it, 6 or 7 different columns. That's going to take a while to update. I think, yeah, do head of data. And it's trying to plot all of that all at once for every single day. No bueno. We don't want to do that. So we're going to actually have to tell it exactly what you want to plot. It's not going to be that easy. Luckily, with Quantmod, there's a really great function that you can just use to extract, let's say, a single column out of this data. You could do data all rows close, that works, and that gets only our close prices. But let's use the Quantmod package, because that's what it's for. CL data, so that'll just get our close. Same thing, right? It's just a little bit more graceful. So now we can plot the close of the data, right? And you think this is going to work, but it's not. Because we've got now just a bunch of different points. We actually want a line graph, so we're going to have to tell R to do that. Type equals, and then the little characters, L. Type equals L, and there we go. Now we've got a line graph. Now that's what we want. But why did Apple stock fall so much here, you think? Like, wow, it went from 600 all the way to 100? I didn't read about that in the news. Well, that's because we're using close prices, which are not adjusted for splits, stock splits or reverse splits or anything like that. It's not adjusted for dividends even. So when you're using that in R, you're going to have to be really careful. In fact, I would say almost never use closing prices alone, unless you're just doing, intraday high frequency trading. But if you're doing that, you're probably not going to need this tutorial anyways. So only use the adjusted close data. So let's do plot AD of data, pass in the type, line, and there we go. There's our adjusted close data. Again, it's the same thing as typing, data all rows adjusted. It's just a little bit more graceful, and then plotting that. It's just a little bit more graceful. And that's much better. There's no crazy drop in the stock price, right? You would have heard about that. That's definitely not the case. So this is exactly what we want. So now we could calculate the simple returns of the data. So first, let's just figure out how many data points do we have. Well, we could do length of AD data. Oops. and run that. And yeah, you can see we've got 2,266 data points. And within each point, you've got the open, high, low, close, volume, and adjusted. For this function, though, I just extracted the adjusted close data. And so that's going to be a lot of returns. So now we could say, let's just calculate the return from this point to that point, right? The total return. So that's going to be, I'm sure you've seen the return formula before. 100 times, here we're going to do the adjusted close of data, and then we're going to index it at row 2266, and then let's say subtract AD of data at row 1. So subtract the first price, right? And then divide that by AD of data at row 1. All right. So in order to do that, you're just going to have to do you're going to do 100 times the last price minus the first price divided by the first price. So you may have seen this simple return calculation, and we're going to run that line, and wow, 844%, that's insane. But the problem is, if we wanted to find the return for each day, we'd actually have to do this, for each day. So let's just do adjusted of, let's just say the second day minus the first over the first, and there's our daily return. Now let's look at the second day and the third day. So that's going to be the third, that's going to be the fourth. So it's going to be the third minus the second, oops, and the fourth minus the third. And this is going to be divided by the second day, and this is going to be divided by the third day, right? And you could go on and on. There's, how many again? There's 2,266. So yeah, good luck doing this and storing that in. You'd have to write a loop to do it or something. No fun. So we've actually got the Quantmod package. That's what this is for. That's the reason why you use R. You've got all of these awesome packages to pull from. So let's go ahead and use that. So let's do daily return of the adjusted close of data. Now we're going to have to do type equals arithmetic, or simple returns, right? We only want the simple returns. And actually what we're going to have to do here is type as.xts of data, xts of data. So this is going to turn data, which is a data frame object, right? Class of data. It's going to turn data into a XTS object. So class of XTS of data. So it's an XTS zoo object. And that's just a little bit better than a data frame, especially when dealing with financial time series data. We're going to cover that later. Don't worry about it, though. But in any case, now we've got our daily returns. All right, so you can see them outputting here. Maybe we want to plot it. Let's go ahead and plot it. Make sure you do type equals line. And there you go. Crazy, right? There's your daily returns for every single day. They're all over the place. That's why you didn't want to calculate this by hand. Use the Quantmod function. So we could also calculate cumulative returns this way. So let's just say plot the cumulative product, cumprod, of 1 plus the daily returns of all of this kind of stuff. So let's just take this here, copy that, and paste that in here. So we're going to add 1 to the daily return, right? Because if you're multiplying by this number and you don't add 1, you're going to get basically 0 for each time, right? So if your return was, negative 2%, and you kept multiplying that by something, it's going to flip-flop from negative to positive, and it's going to get really, really small very quickly. Now, if you did plus 1, you could see that it's basically 1 minus 0.02, so 0.98 times whatever your value was the day before. If you've ever dealt with financial data before, you'll know that this is just something that you do when you plot cumulative returns. So going to go ahead and run this function here. And there you go. You can see that Apple stock has returned, what is that, anywhere from 8 to 900% over this time period. That's insane. You know, there's also another way to calculate returns in financial time series data. You can calculate log returns, and the way that you do that is with diff of log of whatever your data is. So this will be the adjusted close of data. And you're going to want to do this whenever you've got something that's continuously compounding. Maybe you've got savings in the bank that are going to compound every single day. For stocks, for stock returns, that might not make sense. So let's go ahead and plot this. Type equals line. And there you go. There's the log returns, very similar to before, but if you actually calculate the cumulative returns, you're going to see that it's going to be much different. I'll prove that to you later. We could also do the log returns of the normal close as well. CL instead of AD, you know, but look at how bad that is. That's because of the stock split. This makes no sense. You didn't actually get that negative return on that day, so yeah, just don't do that. Don't use the close price. In fact, this is what it would look like if you did that by accident. Yeah, see, look, dropping the cumulative return would drop, you know, all the way down from 8 to basically 1. So be careful. So we could actually calculate the log returns of both the adjusted and the closed data at once if we wanted to. Maybe you've got multiple stocks that you want to calculate the log returns of. So let's just do data, all rows, pass in the vector, close, and then adjusted. And here you can see we've got the close and adjusted. Maybe do head of that just so you can tell. There you go, close and adjusted prices. Now you'd think you could do the diff of the log of that, but it really doesn't make sense. It doesn't work. It doesn't know we want to do each column individually. It doesn't know that we want to get the log returns of the close and then the log returns of the adjusted. Instead, it's saying, you know, should we go across each row, find the log return here, find the log return here, and find the log return there, or should we go down, should we go across? It has no idea what to do. So the way that you do this in R with multivariate data, which is what this is you actually use the apply function. So let's just do apply. Let's take data close and adjusted here. And then 2, that means we're going to apply our argument across the columns. If you put 1 in there, it's going to apply it across the rows. And then type in length. So this is find the length of each of the columns, right? And so perfect. We know this column close has a length of 2,266. So does the adjusted. Now what if I typed 1 instead of 2? Well, that's going through each row and calculating the length for every single row, which is 2, because we've got two columns in each row. So be very careful when you use the apply function, but if you use it right, it's very powerful, as you'll see here. So now we can say apply across the column log, right? And that's going to take the log of each of the rows in the column. Now, if we want to do the diff of the log in order to calculate log returns, we're going to need to nest the apply function. So apply, and then paste in that argument that we had before, and then do, again, 2, and then diff. So this goes through first, says do the log of each of the columns, and then now it says do the difference of the log of each of the columns for each column. All right, real quickly, I'm going to tell you what log returns are. So when you calculate log returns, you're going to assume that it's continuously compounding. It really depends on the situation. You've got the continuous returns equals 1 plus the simple returns, assuming you've already calculated the simple returns, or from price data, you've got the continuous return equals the diff of the log of the data. All right, so I know this looks really crazy here, but it's a very powerful command, and you definitely want to learn how to use this command for a lot of different things. So we can actually save this to a variable. So let's go ahead and copy this, and let's just call this compare add to CL, right? Compare adjusted to close, because we've got our close returns and our adjusted close returns. And now we're going to actually need to make this a data frame. So data.frame of all of that. And there we go. Now we've got our data here. And then we can try to plot it. But that's not going to work. We have to obey the rules of R. It doesn't know what we wanted to plot. So we could say instead plot the first column. So plot the adjusted or the close or whatever it is. And there we go. Now we could say lines, which will add to the plot that already exists. And then just copy this, paste it in here, change the 1 to a 2, and maybe we'll just say do this in red, right? And then run that. So now we've got our adjusted close returns and our regular close returns, log returns. And you may not be able to tell here, but our adjusted price or our adjusted returns here do not cover this. So this isn't red. The adjusted returns are otherwise pretty similar to the close returns, but it definitely is different on the days where there's stock splits. It's also different on days where there's dividends, and it's going to be much clearer when we calculate the cumulative returns. So let's apply one more function here. So let's just do compare adjusted to close, but then call this compare adjusted to close cumulative sum data.frame, and then apply across here compare adjusted to close across each column the function CumSum, which will just add each of the log returns to each other. That's how you calculate cumulative log returns. You can just add the log returns to each other, which is really great. It's fantastic that you can do that in finance. And there we go. There's our data. We can plot it with a line chart here. We'll just say type equals line. And there we go again, trying to, and there we go. See how it starts at 0 instead of the stock price in 2007. So now we're going to add on top of that the adjusted return. So we're just going to do this, copy that, paste that in the lines function, say color equals red, and make sure you change the 1 to a 2 so it's indexing the next column. And boom, there you go. So you can see if you had calculated cumulative returns with the log returns, you've got a whole world of pain coming to you. It's definitely not right. We know that Apple stock's done pretty well recently. In fact, there's no way this could happen. With the red line though, it's definitely going to be a lot more accurate. So use your adjusted close prices. All right, we can also we can also show you the difference between the log returns and discrete or simple returns. So over a long period of time, it's actually going to be a really huge difference. Now, don't worry about this formula that I'm going to type in here. It's just the way that you convert the log returns to discrete returns, and then we're going to have to use we're going to have to calculate the cumulative return this way. All right, so we just calculated the cumulative return of the log returns and the arithmetic returns. You can see the log returns down here in red and the arithmetic or simple returns in black. And the simple returns are much higher than the log returns. That's just the way that it is. Log returns are always smaller than simple returns. Just mathematically, that's the way everything works out. So I know this is a little messy. we could fix that. We could make it much easier to read using a new package called Performance Analytics. So there's a really cool way. So let's go ahead and install that package. So install.packages Performance Analytics. And we'll go ahead and run that line here. And it's going to download that package from the CRAN repository. And make sure you type now library Performance Analytics and run that line. Make sure everything's loaded. We can get rid of this install.packages because we're never going to need to do that again unless we want to update our package. All right, so the Performance Analytics package uses XTS and zoo objects, which are essentially souped up data frames. XTS and zoo objects are perfect for financial time series programming. If you're having a hard time keeping dates when charting or something like that, try using those objects instead of data frames. So just for example, I'll do as.xts, and then going to type in compare add to CL. It looks the same, but it isn't. So that's a data frame, and this is an XTS zoo object. The data underneath is identical, but the XTS object does some really cool stuff when we chart it. So let's in order to get there, we're going to have to make sure that we use daily returns, not cumulative returns. So let's just assign a new object, data equals as.xts of compare add to close. So you could save it as a new variable if you want. You can always convert back to a data frame from an XTS object. And now let's convert back to simple or discrete returns. There's just that formula to do that, and basically we're inverting the formula. So if you've got log returns, you can just do e to the power of the log returns and then subtract 1. Now you've got the simple returns again. And there's our simple returns, and it did that for each of the columns, for each of the rows, and all that kind of stuff. So now we're going to chart it as the cool XTS object, and using a function from the Performance Analytics package. So we're going to use charts.performance summary of data, and then we're going to pass in main, which is just the title. So main equals, and then type in our cool title here. But I guess for this I'm going to say the compare close to adjusted cumulative discrete return, and run that and check it out. On the right, on the top right here, you can see our cumulative return, which you've seen before. Down here, you've got the daily return, which you also saw before. So below that's drawdown, which is essentially how much your portfolio has lost over a rolling window. In this example, it's actually just a single stock. You generally want drawdown to be as low as possible, which means that you want the lines to stay near the top, close to 0. This is actually a rolling var calculation, and I'm going to explain a lot of that in the next tutorial. In that tutorial, we're going to go into a lot more advanced functions, risk management and things like that, ARIMA, calculations, trading strategies, awesome stuff. So anyways, moving on. Let's just say we've got 2 stocks that we want to look at. So let's just ignore everything that we've done here, and let's say we've got Tesla. So let's calculate the daily returns. So using what we know, we can calculate daily returns of the adjusted close, and then let's get symbols, right? Get symbols, and let's get Tesla prices, and make sure you do auto.assign equals false here. Run that. Now we've got Tesla prices. Perfect. Awesome stuff. You can see we've already calculated daily return. We've already got the adjusted extracted out there. We're not having to worry about open, high, low, close price because we don't care about that right now. We could do charts.performance summary. performance summary of Tesla. And you can see this goes all the way back to 2010. Maybe we want to do the same thing with Microsoft. So let's just copy that, call this Microsoft, and boom. Look at that. Using what we know, we're able to extract prices for any stock, calculate the daily returns, extract the adjusted price, and download all of this all at once and chart it in 2 lines for a single stock and 4 lines for 2 stocks. Awesome stuff. That's the real power of R. So you can see Microsoft goes back to 2007. It could go back further if we told the function to, but that's the default. In other words, basically we've got our Tesla, which only starts trading in 2010. And so Microsoft trades for 3 years, and then Tesla will start trading. So what if we wanted to chart these two together? We've got to merge them, right? So first of all, we got to rename the columns, right? Because if we do head of Microsoft, it just says daily returns. So if we merged this with Tesla, that's also going to say daily returns. That's going to get confusing. So let's make sure our column names are set straight here. So let's do call names of Microsoft equals Microsoft, and then call names of Tesla equals Tesla, and then run those 2 lines. Note that we didn't use a vector there. Since it's only 1 column, we've only need 1 column name. So you could do the proper way and just say this. It's the same thing. It's the same thing. But in any case, now we've got, if we do head of Tesla, you can see that it's renamed, and then head of Microsoft, you can see it's renamed there as well. Perfect. So just to prove to you that we've got data going back a different amount of time for Tesla and Microsoft, let's just do dim, which finds the dimensions of our Tesla object. You can see it's 1388 rows by 1 column. Let's do dim of Microsoft, and that is 2266 rows by 1 column. In the beginning, we only have data for Microsoft. So let's go ahead and merge using the merge command Tesla and Microsoft. Awesome. So did it work? Let's do dim of merge of Tesla Microsoft. Now you could save that as a variable and pass that in there if you want. So yeah, it absolutely worked. The number of rows is the same as the number of rows of the biggest object, which was Microsoft. It's 2266. You can see you've got 2 columns there, and we could do head of this object. And you can see Tesla has NAs, and that's going to be NAs for about 3 years, until we reach 2010, where Tesla starts trading. If we look at tail, you can see that Tesla is now trading, right, in 2015. And so what if we only wanted to keep days where both stocks traded? Well, there's a bunch of different ways to do this in R. The easiest way when you're merging 2 data frames is just pass an extra argument in. So now we can say all equals false, which means we're not going to look at all days. We're only going to look at the intersection, basically. And it's hard to see the difference here, but if we do head of that, now you can see it starts in 2010. We've got no invalid days, so there's definitely fewer days, so we can do the dimensions of that and check it out. So we've got 1388 common days, and we have no NAs for any day for any stock. So let's go ahead and save this to a variable. So let's just call that variable, oops, sorry about that. Let's just call this variable Microsoft versus Tesla. All right. So now we're going to go ahead and save that. Now we never have to do that merge again. Right, so we've got that there. Now we can look at the head of that. So note that Microsoft has a return on its first day. Since it traded before that day, Tesla didn't, right? And we calculated the returns before merging these objects, so that's why Tesla has a 0 return on the first day, because, well, there was no day before. So let's go ahead and chart these objects together. So chart.performance summary, and we can do Microsoft versus Tesla. So this function actually automatically applies the intersection merge, by the way. And check it out. We can see that Tesla's got a much higher cumulative return than Microsoft does. The daily returns here is really hard to read when you've got a bunch of different stocks, so kind of ignore that for this. But you can see the drawdown. Tesla's got a much larger drawdown on average than Microsoft does. So overall, Tesla's a more risky security, but it's got a higher return. Microsoft is a less risky security, but it's got a lower return. So how do you balance out return and risk? Well, it turns out that in finance, we've got a measure for that. We've got measures for almost everything, in fact. So have you ever heard of the Sharpe ratio? It's a measure of risk-adjusted return. So there's an easy way that we can calculate that with a handy-dandy function from performance analytics. So basically, the higher the Sharpe ratio, the better. The Sharpe ratio is equal to expected return minus the risk-free rate divided by the standard deviation of returns. Risk-free rate is essentially your yield on U.S. Treasury bonds, because people assume that those are risk-free because hopefully the government's going to never default. All right, that's going to be a little bit more confusing than I wanted to go, but that's just the way that we measure the risk-free rate in finance. So there's a few assumptions that go into our calculation here. Number one is that there's going to be 252 trading days in a year, and number two is going to be that the risk-free rate is about 0.5%. Now, recently, that's pretty accurate. Maybe if you're watching this video in the future, that's much different. So we're going to go ahead and type table.annualized returns. That's a function that comes from performance analytics. Pass in our Microsoft versus Tesla object. Scale equals the number of trading days that in a year that we're assuming, which is 252. Now for risk-free, RF equals 0.005 divided by 252. That's our risk-free rate divided by the number of days in the trading year, the risk-free rate annual. And then this calculates the risk-free rate daily. And there we go. Now we've got our annualized returns for Tesla and Microsoft, which essentially means that, during this time period that we're looking at, your average return per year for Tesla was 50%. Your average return per year for Microsoft was 19%. And, if you had held it over the number of years here, then you would return, 800 or 900% for Tesla and about 200% for Microsoft. Pretty straightforward. The standard deviation is just a measure of risk that goes into our Sharpe ratio calculation, and a higher Sharpe ratio is better, right? So this is saying that by the Sharpe ratio measure, even though Tesla's got a higher standard deviation than Microsoft, it's also got a higher return, and actually Tesla was a better stock to hold during this time period than Microsoft was because it's got a higher Sharpe ratio. Now there's different ways that you could calculate these performance metrics. There's Sortino ratio, which doesn't penalize you for large returns that are positive. And there's a bunch of different ways to calculate this. Sharpe ratio is definitely something that we use in finance all the time. If you work in finance, you know a lot about the Sharpe ratio, so it's definitely something that's good to know. You can look up Sortino ratio yourself if you're interested. There's other metrics that go into calculating risk. Maybe you've got a trading strategy, so you need to look at VAR numbers, value at risk, for a portfolio, conditional value at risk, and we're going to get into all that sort of stuff in the next training series. All right, thanks for following along, and in the next tutorial series, we're going to go into a lot more advanced econometric topics. We're going to use econometric data packages in R. We're going to calculate monthly returns, annual returns, things like that, different periods, perform linear regressions with things like GDP numbers. We're going to introduce you to ARIMA models, which is a time series based model. You're going to use the ARIMA model to predict price movements in stocks. We'll teach you how to use ARIMA in conjunction with your linear regressions to develop a profitable trading strategy, backtest that trading strategy, perform VAR calculations, calculate CVAR for portfolios, and we're going to go into a lot more advanced stuff after that. So please stick around and see what we've got to offer. This concludes the first part of our tutorial series, and if you have any questions or comments as well, please let us know. Make sure you subscribe to our mailing list, and this is Dakota Wixom signing off. Thank you.